Hi class, I wanted to do a quick video for you guys on, this is section 7.3 from the textbook talking about trigonometric substitution. So this, when you first see this type of method, it looks like kind of confusing because there's all these radicals and these crazy integrals, and then we're substituting in for trigonometry. But I promise you actually what it does is it takes these really difficult integrals to solve and it sets them up very easily with trigonometry to integrate them. Right. So we're going to use trigonometric substitution, all right, to evaluate integrals involving this. And sorry for the typo there. So you can use, it's supposed to just be trigonometric substitution to evaluate integrals involving these radicals. So the square root of a squared minus u squared, square root of a squared plus u squared, and the square root of u squared minus a squared. Now here's the thing. A here is just supposed to be a constant. Okay, so like for example, if you see 9 is the same thing as 3 squared. If you see 16, that's the same thing as 4 squared. And u here is going to be some function of x. So we're going to do a very simple integral today in my video of this type right here, this first one, but you can apply it the same way as before. Alright, and what the goal here is to eliminate the radical, alright, by trig substitution, and that is by, like, for example, like this one. A squared minus u squared. Well, like if you have a is 1 and u is sine theta, 1 squared minus sine theta quantity squared is just the same thing as cosine squared. Well, then the square root of cosine squared is just cosine. All right, so let me show you what I mean by that. All right, so for example, if you have a is greater than 0 and we let that u equal a sine of theta, all right, and this is just where sine is positive here. Anyways, if you look here, if we substitute in for u, we let u equal a sine of theta, well then u squared becomes a squared sine squared of theta. Well, they both have an a squared in it now. Factor that out. You get 1 minus sine squared of theta. Well, that's cosine squared of theta. All right, the square root of a squared cosine squared of theta is just a cosine of theta. All right, now the reason it's like, well, okay, great, what did that do? Well, that just transformed this somehow, that got rid of the radical, and that's what we want to do. All right, this is the most important page for today. All right, and as we saw, like, let me go back to the first one. U was a sine of theta. That means the square root of a squared minus u squared is a cosine of theta. Well, for integrals involving this, the square root of a squared minus u squared, we're going to let u equal a sine of theta. Then that means that this integral here is the same thing as a cosine of theta. All right, and you can see here what we're doing is setting up like a right triangle and then using SOHCAHTOA. Like cosine of theta is adjacent over hypotenuse. So square root of a squared minus u squared over a, or multiplying the a over a cosine of theta is equal to this. All right, so we see this type. All right, when it looks like this, we have u equal a sine of theta. Great. Additional, so if you have a squared plus u squared, you're going to let u equal a tangent of theta. Then that means the square root of a squared plus u squared is equal to a secant of theta. And you can prove that just like how I did here, just using these substitutions instead. All right, so for the square root of u squared minus a squared, u is a secant of theta. And then we have the following depending on how the integral is set up in the bounds of integration. All right, we'll focus on this one first here. All right, so let's do an example. Find the integral of dx over x squared times the square root of 9 minus x squared. All right, so first off, what you're going to notice, first, note that none of the basic integration rules apply here. You can't like go to a table, you can't use the power rule, you can't use u sub. It's like, I don't know how to do this. All right, well, here's how you approach trig substitutions. I see the square root of 9 minus x squared. Well, that kind of looks like this integral right here. The square root, 9 is the same thing as 3 squared minus u is just x squared. So it's this one right here. Well, our u is x. So what that means is we're going to use x is equal to a sine of theta. Right, and a here, remember, it was 9, so that's 3 squared, so a is 3. All right, so we use trig substitution. You should observe that this, the square root of 9 minus x squared, is the form the square root of a squared minus u squared. Awesome. All right, so we're going to use this substitution. x, or our u, is equal to a sine of theta. Alright, well that means x is equal to 3 sine of theta. Well then watch what happens here when we go to continue our integration. dx, alright, so dx, the integral or the derivative of x with respect to theta is just 3 cosine theta d theta. That's just taking the derivative of this. The derivative of sine is cosine. This integral right here, this radical, 9 minus x squared, just gets replaced with 3 cosine of theta. And then if you notice, here we had this x squared outside. Well, if I know x is equal to 3 sine of theta, well, just squaring that means x squared is equal to 9 sine squared of theta. Now watch what happens when I substitute this stuff back in. Okay, watch. This original integral, the integral of dx over x squared, square root of 9 minus x squared is equal to, well, dx gets replaced with 3 cosine of theta d theta. Awesome. X squared gets replaced with 9 sine squared of theta, right over here. And this crazy hard radical, so the square root of 9 minus x squared, gets replaced with just simply 3 cosine of theta. Alright, so it's like, well, now it's all in terms of trig. Well, it's actually not that bad. If you notice here, what cancels out? The 3 cosine of theta. It's gone. Alright? I'm going to factor out the 9 in the bottom, so I have 1 9 the square root of d theta over sine squared theta. Well, 1 over sine is cosecant. So 1 over sine squared becomes cosecant squared theta. Alright, so this is the integral now of 1/9, the integral of cosecant squared theta d theta. Well, that's incredibly easy to integrate. The integral of cosecant squared theta is just negative cotangent of theta. Alright, so we're actually not quite done just yet. So just using the trig substitutions, I was able to get this integral here simplified to negative 1/9 cotangent of theta plus my constant of integration. But now here's where the crux of the problem is. The original problem was in terms of x. Now we've substituted into this new variable theta. So what we need to do is go back. So you need to change cotangent back into x. Well, cotangent, if you remember, is cosine over sine. So right here, cosine here, if I divide the 3 over, but it's going to cancel out in both cases, cosine is square root of 9 minus x squared over 3. Sine down here, if I've got to go back, sine is just equal to x divided by the 3 over, x divided by 3. So in both cases, the 3's cancel out. And look, you have it right back in terms of x. Alright? And you can just slap the 9 under with the negative right there. Alright? So if you look back at the triangle in that figure that I had back here, right over here, figure 1, sorry about that, not 8.6, you can convert thetas back to x's as follows. Alright? Cotangent is adjacent over opposite. Well, here's theta, adjacent over opposite. And that's how I got this. Same thing here. Or you could just substitute right back in directly. So it takes a little while to get used to, but this substitution actually makes the integral pretty easy to solve. The hardest thing, perhaps, is just setting up the integral. I just wanted to end on some other formulas that you might want to just hang on to. These, you'll notice, there's no fraction involved. It's just straight up the integral of each of those things. And you can directly integrate them using these formulas right here. You don't need to go through any special type of substitution. Just directly use these formulas. All right, all. Your homework this week is just 10 questions, so give it a shot. And if you have any questions, let me know. Thanks.